And now let's talk about another application of the table constraint, which is the rostering problem. And this problem is solved using an automaton constraint that you can encode as a table. So, what is the nurse rostering problem? Nurse rostering problem is to create a schedule of nurses in an hospital, and the schedule needs to follow some constraints. So there are demands constraints. So for each days, you need to have a given number of nurses, and there are also constraints for the nurses because they can't work more than 24 hours per day. So they can't have a day shift, then a night shift, then a late night shift on the same day. And also some nurses may go on holiday. So if you want to learn more about this problem, you can check the Wikipedia page. You will see lots of stuff there. And so how can we model that? Well, we can model that using an automaton constraint to verify that the schedule for one nurse is valid. And how can we do that? Well, an automaton, what does it take? It takes a sequence. So in our case, a sequence of does the nurse work or not, and so on, and which kind of shift does she do, and it will validate the sequence. How does the automaton does that? The automaton has what we call the starting state, where we start, and then it has transition that goes from one state to other state. It can stay in the same state or goes to another one, and it has also what we call ending state, which are these two, one in this case, and the sequence is accepted by the automaton only if, after reading all the sequence and passing through all the transition, we end up in one of these two accepting states. So in our case, well, we read, maybe we go there, and then there, another transition, and so on. But how can we modelize that as a table constraint? So for that, we will need what we call the transition matrix. So the transition matrix, it takes the IDs of the states and the values of the transition, and for each combination of a state and a value, it will give the next state where it goes. So here, if we have state 0, here we have value 1, we see in the automaton that we stay in the same state, so the matrix here, it's 0, we stay in the same state. So to verify a full sequence, so for example x, y, z, we first start at 0, then we look at the value in x, which correspond to one of the transition. We end up at the second state, then we look at the transition, so the value of y. We end up in a third state, and then we look again at the transition, so z, and we end up in a last state, and then we need to look if the state is an accepting one. So here we can define the state after reading x, the state after reading y, and the state after reading z, since states in the initial state is always 0. And we can define the state after reading x as the transition matrix from state 0 with value x, then state y as the transition from state x to n value y, and state z as transition from state y with value z. And then we just need to check, does state z is accepted or not? And to encode this transition, we will need what we called an element 2D constraint, and we can encode it as a table. How do we do that? Well, for each of the elements in the transition table, we will create a line in the table. So in this case, here we have this element, which has these two elements. So 0 for x, which is in the automaton constraint, it's the state. Here, the second one is 0 also. In the automaton constraint is the value. And here we have the result, so the content of the square, which is in the automaton constraint, the next state, and so on. So each of the square that we have here, it's one of the line. And then we just need to input the table constraint as a constraint, and it's working. And so for the automaton constraint, we have to put multiple element 2D constraints to model all the automaton, and then it's perfect.